All right, thanks very much, and thanks for coming, everyone. Yeah, so again, the structure will be that we'll have 4 talks, Tuesday, Thursday this week, and next week as well. And then there will be a problem set that will be posted probably sometime today, and so that'll sort of be covering the material or relevant to the material from this week's lectures rather. And so there'll be a problem session next Wednesday, so Wednesday of next week at the same time. And that'll be led by Carissa Sloan. And so then there'll be a second problem set corresponding to the lectures for next week. And then there'll be, again, a problem session the week after on the Wednesday. All right. So, yeah, so we're going to be talking about the equivariant slice spectral sequence. And so today, my goal is to start by reviewing G spectra. So the slice filtration, the slice spectral sequence, this is something happening in the world of G spectra. I'm not assuming everyone's an expert in all things equivariantly stable. And so we'll start with a discussion of that. And then we'll turn to KR, which is kind of a motivating example for the slice filtration. I mean, in fact, that's that Dan Duggar was sort of grappling with this and came up with the slice filtration in his thesis work. And so that's where we'll start as well. And so then we'll talk about the slice filtration, especially as discussed by Hill, Hopkins, and Ravenel. And for today, we'll focus on the case of the cyclic group of order 2, but next time we'll look at the more general definition. And so once we've done that, then we'll turn back to KR and look at what the filtration actually looks like in that example, and we'll discuss the slice spectral sequence in that case. And please do, if you have questions, I mean, I'm going to try to monitor the chat, but please do feel free to jump in and ask questions. If I'm just talking at everyone for an hour, that's not ideal. So, all right, so let's start things off. Again, diving into the world of G spectra. And so the first thing I want to say is that, okay, we have something called a suspension G spectrum. If we start with a based G space, then there's something we can construct. It's called a suspension G spectrum. And so in particular, if we apply this to the space S0, so 2 points with a trivial action, then we get, well, the sphere G spectrum. And so, we'll be using this pretty often to just sort of think about a base G space as a G spectrum. And this is a nice construction. It's a strong monoidal functor. So in other words, if we take a smash product of 2 base G spaces and then produce the corresponding suspension G spectrum, well, that corresponds to first producing the suspension G spectra and then smashing those spectra together. Okay. And the next construction or next thing I want to mention is, this is going to show up quite a bit. If we have a G representation V, so again, that's, we have a finite dimensional real vector space with a linear action of our group G, and G will always be finite in our story, by the way. Then we can 1 point compactify that vector space, and then we get what's called a representation sphere. Okay. And one thing that's important in this story, or at least in the version of G spectra that we're working with, is that if you take one of these representation spheres and then produce the associated suspension G spectrum, that will turn out to be an invertible object in our category. Okay. So what that means is that, well, there's some other G spectrum, let's call it S minus V. And if you smash that with SV, and so again, I'm already abusing notation. What I really mean here is this suspension spectrum right there. Okay, so if you smash that with this new thing called S minus V, then you get back the sphere G spectrum. And so now I'm noticing I should have probably put a subscript G there. Okay, so anyway, so these representation spheres become invertible, and that's like, in the non-equivariant case, we have not only positive SN spectra, but also negative SN spectra. And so this is just the generalization to the equivariant world. All right, and so just some notation now, this operation of smashing with SV, is pretty important. And so we just use sigma V to denote that. And similarly, sigma minus V is going to be smashing with its inverse. All right. Any questions on this first slide here? All right, and so I'm gonna, of course, when you move from slide to slide, one thing that we suffer from, not being at chalkboards is that we lose some information. So I will try to sort of retain some information from the previous slides on the left, but it's not perfect. So again, if you want me to go back, please feel free to shout. All right, so another thing that's important here as we think about G spectra, whenever we have a subgroup, and let me write that here. So H, a subgroup of G, then we're going to want to think about the interrelation between G spectra and H spectra for various subgroups. And there are constructions that allow us to go back and forth. And so, for instance, if I have a G spectrum, I can restrict down to an H spectrum. And so our notation for that will be this down arrow notation. So we're restricting from G down to H, and that produces an H spectrum. Okay. And so here, a lot of the intuition comes from the world of spaces. If you have a G space, and now we have some subgroup of H, you can just restrict the action down to the subgroup, and that gives you a perfectly well defined H space, right? A space with an H action. And the point is that, well, there is an analogous construction in this world of G spectra. Okay. And at this point, you might be complaining that I haven't really told you what G spectra are, and that's true. Okay. So there is a construction in the other direction. And it's in fact an adjoint functor, and this is called induction. We'll be using the up arrow notation for that. And in the topological setting, this is often written as smashing over H with G, and it's inducing up. We start with something with an H action, and we're creating now something with a G action. Right? And so one of the most important cases is when H is the trivial group. So then we're starting with something with no action, and now we're producing a G thingy with a free action. All right. So that's one important construction that relates H spectra and G spectra. But another thing we can do, and again, we can think about the world of spaces, if you have a non-equivariant space or an ordinary space, you can think of it as a G space by just using the trivial action, right? And so again, there's an analog of that in the stable world. Sometimes that construction is known as inflation. So the idea is that we're sort of, we have the quotient map from G down to G mod G, and we can view that as sort of deflation. And sort of the opposite of that is inflation. So I see a question in the chat. Induction is the left adjoint. Yes, it also happens to be the right adjoint in this case. This is kind of a funny situation. So yeah, this is left and right here, adjoint. Which turns out to be super useful. This is something called the Bert-Muller isomorphism. Says that it's adjoint in both directions. So that's something that we're not used to in the world of spaces. In the world of spaces, the adjunction goes this way. I mean, the induction is the left adjoint in the world of spaces, restriction is the right adjoint. But in the world of spectra, it's in fact both left and right. We'll see this sort of occurring several times in various guises. All right, so here, again, we said inflation. This is, we can think of this as creating something with a trivial G action. And this is a left adjoint, and the right adjoint is a fixed point construction. Again, that's totally analogous to what happens in the world of spaces, right? We have this trivial action functor, and the right adjoint to that is the fixed point construction. Now, one thing we have to be a little bit careful about is that in the world of spectra, there are various things that are called fixed points. And so this version is what's called the categorical fixed points. We'll look at another version in a minute, but so this is one kind of fixed points, and it's adjoint to inflation. All right, and then the other thing is you can actually combine these. I mean, if we have a G spectrum and we want to think about the H fixed points of that G spectrum, that would make perfect sense at the world of spaces. And to do that at the world of spectra, what we have to do is first take our G spectrum, restrict it down to H, and now it makes sense to use our H fixed point functor to produce an ordinary spectrum. Okay, so those adjunctions combine, and so now we get this H fixed point functor. All right, great. So again, that's the formula, the H fixed points of a G spectrum. You restrict and then take fixed points. All righty. So again, if you're new to this, you might be wondering, how do these various functors combine? For instance, if I take a G space and I create the G spectrum and then take fixed points, oh, does that correspond to just taking the fixed points of the space and then creating a spectrum for that? No, it doesn't, at least not for this version of fixed points. And so here's an example. One of the simplest examples we might consider, if we take the C2, G equal to C2, and we take S0, right, as our space. So this is the sphere G spectrum. It turns out if you take the categorical fixed points of that spectrum, and this is not meant to be obvious, I'm just stating that this is what turns out to be the case, is that you get this one piece, which is what you might have hoped for, but that's not all there is to the story. There's another piece to it. Okay, this is what's known as the Tom-Deke splitting. And there's an analogous but slightly more complicated formula that works for any group and any suspension spectrum, but I just wanted to give it in the simplest case. So just something to be aware of. These fixed points, these categorical fixed points, don't behave quite as simply as you might expect. Now, there is a sort of a fix to that. There's a different version of fixed points which does have the property here that we might expect. Okay, and so to introduce that, let's first consider a G space. This is called E tilde P. So the P here stands for proper subgroups. And this is a G space with the property that if you think about the fixed points for various subgroups, it's empty if we look at the fixed points for the whole group, but it's contractible if we look at the fixed points for any proper subgroup. Okay? And it turns out that you can always produce such a space. And in the case of C2, here is a construction of it, but again, these always exist for any group G. So for C2, you take the infinite sphere, S infinity, but now you equip it with the antipodal action. Okay, and so now as an underlying space, it's contractible because S infinity, the space, is contractible. But this is a free action, so there are no fixed points. Okay, so that's why this counts as one of these spaces. All right, and so with this space, then we can sort of crush it to a point, and so that'll go here, and then we define this new space E tilde P, which is the cofiber. In fact, on the problem set, I ask you to think about a particular model for this, but anyway, right now we're just giving the sort of the general construction, and it turns out we can use this E tilde P to define a different version of fixed points. And so these are what are known as the geometric fixed points. So again, they behave the way we might hope with respect to suspension spectra. We'll see that on the next slide. But so here's the definition on the lower left. You take your X and you smash it with this G space. Again, this G space is sort of, it's, it's this cofiber, but what this does is it's going to sort of throw away all the information at the proper subgroups and retain only information at the whole group G. So you first smash it with that, so that throws away a bunch of information, and then you pass to fixed points. So this gives a different construction. So this is what's called the geometric fixed points. It goes from G spectra to ordinary spectra. And there is a map back in the other direction. It turns out to be the right adjoint of geometric fixed points. And so it's combining inflation with this sort of geometric idea. And so I call it geometric inflation. But the formula is, okay, you just do the inflation, right? So you create the thing with the trivial action. But as we saw up here, that's typically going to have some junk there that we don't care about. And so you throw it away by smashing with the EP tilde. So that's the construction. It turns out, I mean, that this right adjoint here is fully faithful. It actually embeds spectra inside of G spectra as the image of this functor. And that image are what are sometimes called geometric G spectra. So they're sort of coming from this geometric situation here. And so we'll see that coming up again later. All right. All right, so again, we just saw this geometric fixed points construction. And so here's some of the key properties of geometric fixed points. So again, it fixes this problem that we saw for the categorical fixed points, namely, it does behave exactly as you might hope, right? So the geometric fixed points of a suspension spectrum is just you first take the space level fixed points and then spectrify. It also behaves well with respect to smash products, as it turns out. So the geometric fixed points of a smash product is the smash product of geometric fixed points. The geometric fixed points of the sphere is just S0. I mean, that follows from the first item as well. So this is a well-behaved version of fixed points, at least from the point of view of these properties. Okay, so again, we'll see this geometric fixed point showing up later. And it also is related to the categorical fixed points because, well, remember we defined this EP tilde as a cofiber. And so, by its definition, there is a canonical map from S0. And if you smash that with some G spectrum Y and then pass to fixed points, it produces this canonical map from the categorical fixed points to the geometric fixed points. Okay, so we always have this comparison map. It's usually not an equivalence, but just something to be aware of. Okay. All right. So then the next thing I want to mention is the notion of a MackieFunctor. And so why are we considering this notion? Well, for ordinary spectra, we have homotopy groups. Okay. And it turns out that in the equivariant world, we have a richer algebraic structure. And so how does this come about? Well, if I have some subgroup H of G, then I'm going to define pi n h of this G spectrum X to be first passed to the fixed points and then take pi n. Okay, so this is, we have this ordinary spectrum now. We can take the abelian group pi n of that. That's a perfectly good thing to consider. But then it turns out, if you think about it, as you vary your H, there are maps between these. For instance, the G fixed points is going to map to the K fixed points whenever K is a subgroup, etc. And so you start to notice, hey, I have these maps like this. And so those are going to be what are called restriction maps and less obvious, but there are also maps in the other direction, which are known as transfer maps. Okay, so that's part of the data of a MackieFunctor. So we have these abelian groups indexed by subgroups, K and H of my group G. And there's one more piece of data, which is the action of what's called the Weil group. So if I look at the spot labeled by my subgroup H, it turns out that's going to be a module. There's going to be an action of this Weil group for H. The definition of the Weil group is it's the normalizer mod H. So again, what you might first expect is that there's an action of G mod H, but then you notice, oh, that doesn't make sense because H is not necessarily a normal subgroup. So G mod H is not necessarily a group, but this is kind of the next best approximation that actually does make sense as a group. It's also not totally random. I mean, so the Weil group is just the automorphism group in the sort of G equivariant world of the orbit G mod H. Okay, so it doesn't, so it has a sort of natural appearance there. Okay, and so then, that gives rise to an action. Anyway, so this data together is what's called a MackieFunctor. So I'm going to sort of display it here all together. So this is, this kind of picture is how we display MackieFunctor. So I have a group up at the top, and then for each subgroup K or H, I'm going to have another abelian group, and I have restriction maps and transfer maps between them, and I also have Weil actions at each spot. Okay. At the bottom, the Weil group is the whole group G, and so at the bottom I have a G module, but at the intermediate spots I have actions of some smaller groups. And there are a bunch of axioms or properties this has to satisfy. I'm not going to go into those, but anyway, so it's this data plus some axioms. So rather than spelling out the axioms, let's just look at some examples. And so one thing we might wonder about is, I told you that pi n of any G spectrum is always a MackieFunctor. All right, so we might think about pi naught of the G spectrum S naught. And it turns out that this is what's called the Burnside MackieFunctor. And so at level H, so A of H, this is the free abelian group on the set of G orbits, so H orbits, I should say, up to isomorphism. Okay. And so here on the right, I've displayed it in the case of a cyclic group. So at the bottom, we have the Burnside ring of the trivial group, which is just, there's only one orbit. It's just a point. And so we have just a rank 1 Z. And at the top, so now we're considering the Burnside ring of the group CP. And the point is that there are two types of orbits. There's the trivial orbit and the free orbit. So we get a rank 2 group at the top. And the restriction map, at the top we have an H set. And when we restrict down, we sort of forget about the action, just think about the underlying set and just count the cardinality. Okay, so 1 is a set of size 1. And so that's where this 1 comes from. And CP is a set of size P. And so that's where that P comes from. Okay, so I've written that restriction map as a matrix. And then the transfer map is going to, it sort of takes a set and then creates a free CP set. And so again, that's what this is saying. So 1 goes to the free orbit. Okay, so that's an example of a MackieFunctor. It's the Burnside MackieFunctor that plays an important role, although it will not figure prominently for us. So instead, something that will be more important for us is the following construction. So if you start with a G module algebraically, so something with an action of the group ring ZG, there are actually two different ways to produce a G MackieFunctor from this. One is to take your G module and at every level H, just think about the fixed points with respect to H. Okay, that's a perfectly good abelian group. And again, as you allow H to vary, you can see that the various fixed points include inside each other. And so those restriction maps that we need for our MackieFunctor are just the inclusion maps. So that's pretty simple. There are also transfer maps in the other direction. Those are less obvious to see. Essentially, you just kind of sum up over the actions. But yeah, we won't sort of spell that out as much. Anyway, so this is one construction, but there's also a different one, and we'll denote this one by Q. And so instead of taking fixed points, you pass to orbits, right? So you have your module with a G action, and at every level H, we just mod out by the H action. And for that one, as you vary H, there are quotient maps you can consider, and those will be the transfers. And again, in this version, the restrictions are perhaps less obvious, but again, there's something you can define that works there. All right, so these are two different ways to produce a G MackieFunctor from an algebraic object, namely a G module. And so in particular, let's look at a couple examples of this. And let me say that for us, this F construction will be much more relevant. It'll show up more often. And so we're going to kind of suppress it from notation. So typically, if I have a G module, I'll just write sort of the underline with that G module, and I'll always mean the fixed point construction unless I say otherwise. So in particular, if we start with this trivial Z module, this trivial module, and here I should say I'm considering the group C2. I guess in both of these examples down here. Then okay, we have C2 with we have Z with a trivial C2 action, and so the fixed points is again just Z because we don't, there's nothing going on, and then the inclusion, is the identity map. And in this case, you can again, I didn't tell you how the transfer is defined, but it turns out it's multiplication by 2 in this case. Right? And so this is what's known as the constant MackieFunctor. I mean, you could really do this with any abelian group. I chose Z because it's sort of central role, but you always have this construction of what's called a constant MackieFunctor, where the restrictions are always the identity. Okay, and then the other one I want to look at here is, what if we take a Z with the sign action, again of C2? Okay, so again, the non-trivial element of C2 is acting by multiplication by -1. And so that's a C2 module. But this one doesn't have any fixed points. So at the top, I have the 0 group. And at the bottom, I have my module, but now I'm remembering the action. And so that's another MackieFunctor. And again, we'll just sort of denote it by Z sigma for this MackieFunctor. Okay. Any questions? All right, so we're almost done with our review of G spectra. So the other thing to note is that when I have a G MackieFunctor, then just like in the non-equivariant world, if I have an abelian group, I can produce an Eilenberg-MacLane spectrum. That also holds true in the equivariant world, right? So if I start with a MackieFunctor, then there's a corresponding Eilenberg-MacLane spectrum. And it doesn't have any homotopy MackieFunctors except for degree 0, where it is whatever MackieFunctor we started with. Okay. All right, and then let me also just point out there's a notion of pi star isomorphism in this context, which kind of measures the equivalences. And so again, what we're saying is that something is considered an equivalence, or in other words, it's going to be an isomorphism in the homotopy category, exactly when it induces an isomorphism on the MackieFunctors for every integer z. Okay, and it's not so hard to see that this corresponds precisely to just being an equivalence on all of the fixed point spectra. And again, this is the categorical fixed points for every subgroup H. All right. Right. So this is the end of our review of G spectra. We're going to talk about the example KR in a minute. But again, any questions about some of this preliminary stuff? I know it's a lot, but it's going to sort of keep coming back, and as we see more examples. Okay, let's see. So here we have Atiyah's real K theory, which is the, like I said, the motivating example for the slice spectral sequence, at least for the group C2. So what's the idea behind this spectrum, or this equivariant spectrum? So this is going to be a C2 equivariant spectrum. And the idea is that, okay, let's think about ordinary complex K theory. And this is the periodic version. This is the spectrum. And so this is built out of complex vector spaces, complex vector bundles, and so on. But the point is that, okay, we have an action of C2 on the complex numbers itself via complex conjugation. And if you keep track of that, then you can think of Ku as something with a C2 action, right? And so then this is the spectrum Kr. Okay, it's just Ku, but keeping track of this complex conjugation action. And then sort of by definition, the underlying spectrum of this is Ku. Okay. And so again, this was introduced by Atiyah. And again, what he showed is that, well, the fixed points are Ko. Right? And then, so then this leads to a sort of a real conflict in terminology. So, this is Atiyah's real K theory, but now the fixed points are real K theory in this other sense. And if you say them out loud, you can't distinguish. So in literature, I mean, often people will use a capital R for this kind of real K theory, and then this would be the lowercase r, but it's not great. But anyway, so just something to be aware of, and always ask for clarification if someone's telling you about real K theory. All right, so what do we know about this C2 equivariant spectrum? Well, we know the underlying and the fixed points, and Bott periodicity. One of the first things you learn about K theory is that the homotopy is periodic, right? So the underlying is Ku, and that's 2 periodic, whereas the fixed points are Ko, and that's an 8-fold periodic thing. That's great. I mean, so in fact, I mean, if we sort of forget a little bit down, I mean, 2 periodic is also 8 periodic, and so both of these are 8 periodic. And so we learn, oh, our MackieFunctors for Kr have an 8-fold periodicity. Great. That's pretty good. Most spectra don't have anything like that. But the wrinkle is that there's another thing to keep track of here, which is an equivariant kind of Bott periodicity. And so here we go. So this says if we suspend by rho, and I'll say what rho is in a second, then we have a periodicity in that sense as well. Okay, so that's a different periodicity. These are just sort of integer suspension of periodicity. So here's something different. So again, what's rho? Well, we can think of it, it's a representation. It's a 2-dimensional representation. You can think of it as the complex numbers with that complex conjugation action. But it also turns out to be isomorphic to the regular representation. And so again, what is the regular representation? You can think of it as just take the free orbit C2, so it has 2 points, and turn that into a vector space where the 2 points become the basis elements, and then we get a canonical action, and that's the regular representation. Anyway, so this is an important representation, but it's two-dimensional, and we have a periodicity in this sense here. Okay, so so now this is what spurs the analysis or the the genesis of the slice filtration, really. So the issue is that we have this real Bott periodicity. So again, that's this formula here. But unfortunately, if we just look at the the MackieFunctors, like I was telling you about before, we're not seeing this sort of two-dimensional periodicity. It's a sort of two-dimensional periodicity, but it's not represented in this eightfold periodicity, right? And so the slice filtration is a response to this, right? Where you want to produce something. So it's a different filtration for C2 equivariant spectra. And at the underlying level, it's going to correspond to the usual sort of Postnikov filtration, right? Where we just think about the homotopy groups at the underlying level. But we also want something that interacts well with this, this suspension by rho. And again, it should be compatible with this Bott periodicity in the KR case. And so that's a little bit of a vague statement. I've put a more precise statement down here, which is really the interaction that we want. And so again, the first time you see this, it can be a little bit not so obvious to parse. And so what is this formula saying? Well, suppose I start with some equivariant spectrum. So again, today it's a C2 spectrum. And then I suspend by the regular representation. So that's like kind of two-dimensional suspension of X. And then I'm going to look at my filtration. So again, we haven't defined the filtration yet, but this is the motivation, right? We're going to want our filtration. We're going to look in degrees between n+2 and k+2. So n+2 here is the upper bound, whereas k+2 is the lower bound. Okay. And what we're going to want is that, well, this is basically just a shifted copy of if you start with X and looked at the filtration between K and N. And so here now we're shifting it back up. That's a sigma rho. Okay. So again, what this is saying is that suspending by the regular representation just shifts your filtration around. Okay. So this is, if we just use the filtration by homotopy MackieFunctors, this doesn't work. And so this is a different filtration which does have that feature. That's the kind of the main motivation here. All right. So any questions about the last couple of slides on Atiyah's real K theory? Yeah, so someone asked, what is the P notation here? So unfortunately, the P notation is what's used in the Postnikov filtration, and it's a reasonable thing to use there because, oh, there's a letter P, okay? And then, so then we have this notation that's been around because it's used for the Postnikov filtration, and now we're using a new filtration, and, well, people have been using the letter P for it, even though there is an equivariant Postnikov filtration, and anyways, so yeah, so probably a different letter should be used here, but anyway, this is sort of what's become standard. And I think in Duggar's thesis, he sort of has two different fonts for the two different versions of P. Like one of them's bold and one of them's regular font, if I recall correctly. Yeah, but yeah, so the P doesn't really stand for anything except this is what's used in other filtrations. Thanks for that question.
Sorry, I have a quick question.
Yeah.
Is it possible to detect this R-Bott periodicity by using, say, like homotopy groups out of, or where instead of out of spheres with a trivial action, we say use out of representation spheres, like out of, say, the representation sphere for the regular representation?
Yeah, I mean, yes. So what you're alluding to is, I mean, there's this idea of ROG graded homotopy groups. So that's not something that I'm talking about quite yet. That'll show up more sort of next week. Yeah, so again, the question is, what if so homotopy groups are mapping out of spheres, and what if we map out of representation spheres instead, And that's a good and interesting idea that turns out to be useful, but that's not what we're doing just yet. Thanks for that question. All right, so again, still part of the motivation, what we're looking for, sorry, there's another question. Is the homotopy category triangulated as a category? Sure is, yeah. All right, so yeah, what we're looking for is fiber sequences of this shape. And so again, here we're just thinking about what happens for the Postnikov filtration classically. So here we would, classically we'd have some spectrum, and this is like the N connective cover, which only has the homotopy in degrees N and higher, and then the co-fiber where we've truncated, and this is only going to have the stuff below degree N, right? So again, this is sort of what we see in the classical Postnikov filtration, and now we're defining a new filtration, but we're going to want the same kind of setup. Okay, and so here I have just a slightly more sort of refined version of that. So here, I have 3 indices J, K, and L. You can think of this one up here as kind of the unbounded case. And when I look at this kind of picture, the way I'm imagining it is, in the middle, I have something sort of from level J all the way up to level L, and maybe here, there's a level K in between. And this thing has sort of the stuff up here, whereas this one has the stuff down here. Okay, that's in my mind, that's the kind of thing I imagine. So again, we sort of cut off the stuff in higher dimensions, and we get something concentrated in lower dimensions, and the fiber has the higher dimensions. Okay, so that's the kind of thing we're going to get. We haven't defined it yet, but that's what we're heading towards. All right, and so one important case is when if L and K+1 are the same, then this fiber here is concentrated in a single dimension, and that's what is called a K+1 slice when we have something which is in a single dimension in this slice filtration, which we're about to define. Okay, all right, so again, that's all the motivation. So now let's actually give the definition. And I should say that the definition that we're using is what's called the regular slice filtration. So again, the filtration was first defined by Duggar and then taken up by Hill, Hopkins, and Ravenel in their covariant invariant work. But the definition we're giving is not the one that you'll find in the HHR paper. Instead, we're using a variant that was introduced by John Ullman in his thesis, and it's called the regular slice filtration. It's a little bit simpler, and I find it more convenient. Okay, so what is this filtration? Well, so inside our category of G spectra, and so again, today, if we're just doing C2, we're going to define a subcategory, which is, it's going to be the category of sort of N-connective things in the sense of this new filtration. Okay, so now we have to specify, well, what do we mean by N-connective in this sense? And there's a couple ways to say it, but what we want to do is we're going to take the regular representation spheres, but we're going to take the ones that are dimension at least N. Right, so remember that rho is 2-dimensional, and so this thing has dimension 2k. And so in our category of things that are at least N, we're going to take the representation spheres of dimension at least N. And the other thing we're going to do is we're going to take all of the induced spheres of dimension at least N. Okay. And so again, remember, in this case, inducing up from the bottom is just the same as smashing with the free thing. So that's the induced sphere is just this thing. It's the free sphere. So we're taking those and we're building a subcategory that contains those. Okay, and there's different ways to talk about it. It's the smallest localizing subcategory containing those in the sense of triangulated categories. But sort of more concretely, you take the smallest subcategory. It's a full subcategory. It's closed under isomorphisms, meaning if you have one thing in the category and something else isomorphic to it, then okay, that other thing must be included as well. It's closed under wedges and cofibers, which tells you it's closed under homotopy colimits. So again, that's telling us we're allowed to build anything using these basic building blocks. It's also closed under extensions. Okay, so that's the definition of this subcategory. And again, this is going to be our notion of sort of N-connective in this new sense. Okay. So this is not the same as N-connective in the usual sense, except sometimes it is. In particular, in degree 0, it happens to be the same. Okay, so being n connective in this new sense, when n is 0, is the same as being connective in the usual equivariant sense, meaning that your underlying spectrum and your fixed point spectrum are both connective spectra. Okay. And it turns out it's also true in the case of 1, but then in other dimensions, it's certainly not true. Okay, so great. Now we've constructed these subcategories. And so now we know what at least n is. What is less than n, or at most n minus 1? Well, again, if we think back to ordinary spectra, something in the Postnikov filtration, which is less than n, means that it doesn't have any homotopy groups in dimensions n and higher, meaning we can't map in a sphere of dimension at least n into our spectrum, right, or space. And so we kind of use that same definition here. If we have a W, which is at least n in our new sense, and we don't have any maps from such W's into X, then okay, then we'll say X is less than n. Okay. So again, the motivation, intuition really comes from the classical Postnikov filtration. And again, the terminology, I mean, there's different terminologies you'll find, but slice n minus 1 co-connective, and this, it's kind of really dual to the connective language. So that's the terminology I prefer. Okay, so now we know what at least n means, we know what less than n means, and then let's actually produce our filtration. And the idea is that we can just use the general machinery of Bose field localization. Okay, and so we have this, we know what it means to be less than or equal to n, and you can just use the general machinery to produce a truncation functor, p upper n, and it'll take in a G spectrum. And again, today G is just C2, and it'll spit out a G spectrum. But then the output will always be at most n, just from the general machinery. And you'll also get a map from your original G spectrum to this truncation. And it'll be a universal such map. And then we can define the P lower n plus 1 as the fiber. Okay. So now by definition, right, and then it takes some work to actually see that that fiber is at least n plus 1 in this case. So again, these are the kinds of things that HHR prove when they really work out this slice filtration. But these are ways that you can define it. So again, use the general machinery to produce this P upper n, and you define a P lower n plus 1 as the fiber. In particular, you can produce these P upper n lower k. So again, those are things between level k and n by first sort of truncating and then taking a sort of slice cover in this sense. All right. So again, a lot of this is sort of coming from general techniques once you set up the categories. All right. So what are some properties of this? So again, many of these are in the Carver HHR paper. And for instance, the zero slice is pretty easy. And the formula is you just take the pi naught of X and you take the corresponding Eilenberg-MacLane spectrum. That's the same thing we would see in the Postnikov filtration. So again, in this particular moment, they agree, but in general, they don't. And so here we can see in level 1, they don't agree because here's a formula, which is not what we get for the Postnikov filtration. And it says that the one slice of X, you take the pi 1 of X. Now this is some MackieFunctor. It has its restrictions and transfers. And we're going to force it to have injective restrictions by modding out by the kernels. Okay, so this is a construction you can do on a MackieFunctor. It's a new MackieFunctor. You produce the Eilenberg-MacLane spectrum and put it in degree 1, and that's the formula for the one slice. Again, let me warn you, if you look at HHR, this does not agree with what they say because they're not using the regular filtration. They're using what's sometimes called the classical filtration. Classical here means 2009. And so it's off by 1. They have this kind of formula for the -1 slice, and this is kind of what you'll see for the 0 slice in their setup. So just a warning there. Okay. And then we do have this formula that was the motivating, one of the motivating formulas. Another thing that's very useful is suppose that we have a fiber sequence where the target is at most n and the source is, or the fiber is at least n plus 1. This is something that looks like it could potentially be a slice sequence. Again, in the Postnikov setting, it would be pretty clear that this must be the Postnikov factorization or filtration. And again, this is another thing that Hill, Hopkins, and Ravenel prove, is that such a thing is in fact a slice filtration. So in this case, the thing on the left must be the n plus 1 slice cover of y. The thing on the right must be the n slice truncation of y. So if it looks like a slice tower, it is a slice tower. And this is super useful. Again, you just produce something that looks like it might be the slice tower, and then you're done. Okay. All right. So, okay, so now we've defined the filtration. We have this motivating example, and let's see what it looks like in this case of the K-theory. All right. So here's our C2 equivariant spectrum. Again, we said that the fixed points are KO and the underlying is KU, right? And so here I've drawn some maps. There's a map from KO to KU, which is sort of the complexification map, right? It turns a sort of a real bundle into an associated complex bundle. And that corresponds to a map from the K-theory spectrum KO to KU. There's also a realification map going back the other way, which, if you think about a complex vector space of dimension n, that now becomes an underlying real vector space of dimension 2n. And same thing with vector bundles. Anyways, and so if we passed a pi naught on this sort of diagram of maps of spectra, it turns out that we get this constant MackieFunctor that showed up before. Turns out there's a trivial action down here, restriction is 1, and transfer is 2. And so that's pi naught of KR. And so because of this property that's on the left over here, right? If we know pi naught, then we know the zero slice, right? So the zero slice of KR is this Eilenberg-MacLean spectrum with the MackieFunctor Z, the constant MackieFunctor. All right, let's think about the one slice. So for the one slice, again, there's this formula here that we should think about pi 1, and then we're going to need to make the restrictions injective and so on. What's pi 1? Well, okay, what's pi 1 of KO? Well, that's Z mod 2. So there we go. What's pi 1 of KU? Oh, KU is concentrated to even degrees. There's no pi 1. Okay, so here's our MackieFunctor. It's Z mod 2 at the fixed point level and 0 at the underlying level. Again, this is one of these geometric constructions. So I refer to this MackieFunctor as little g because it's a geometric MackieFunctor in the sense that it vanishes at the bottom. Okay. Hill, Hopkins, and Ravenel call this B10, but yeah, anyway, I refer to it as G. So there we go. We have the MackieFunctor. Now for the one slice, we're supposed to take this MackieFunctor and mod out by the kernels of the restrictions. Well, the kernel of the restriction here is that whole Z mod 2. If we mod out by it, we get nothing, right? And so what we see is that the one slice is, this MackieFunctor is 0. So h of 0 is trivial, and suspended by 1 is still trivial. So we get no one slice. Okay. So we have a formula for the 0 slice and a formula for the one slice. All right, we're going to keep going, but any questions? All right, so we have 0 and 1. What about 2? Oh, and so by the way, like I said, Duggar considered this in his thesis, and so you can read about it there. There's also not the Corvair paper, but a different paper of Hill, Hopkins, Ravenel, where they discuss this example in detail. This is their paper on the C4 analog of real K-theory. So they have a nice discussion of this example there. All right, so what about the 2 slice? Well, so now we're going to use our other formula, which tells us that suspending by rho just shifts your filtration by 2. And so again, this is a very useful formula. The 2 slice is just the rho suspension of the 0 slice of the rho desuspension. This would be true for any spectrum. This is just reinterpreting this formula here. But where we win is that, hey, we know what the rho desuspension of KR is, because that was our real Bott periodicity. the row d-suspension of KR is just KR itself. And we know the 0 slice, we just computed it. And so now here's our formula for the 2 slice. It's just sigma rho of HZ. Okay. And the same idea gives you the 3 slice, that same periodicity thing. It's going to be, we just need to compute the 1 slice of the row D suspension. Well, that's the 1 slice of KR itself because of the periodicity, and that vanishes. Great. So, and now you can see that the pattern continues. We can see that we're going to have a certain row suspension of HZ in every even dimension, and we're not going to have any odd slices. Okay, so just from those few basic properties, we were able to find all of the slices of the real K-theory, again, using the Bott periodicity. That was very important. Okay. All right, so what I want to end with is just sort of displaying what the spectral sequence looks like for this. And for that, it's a little bit more convenient to work with a connective version, just takes up less space. And fortunately, I mean, connective cover in the equivariant world just means connective cover at the underlying and fixed points. But we happen to know that the connective cover is the same as the slice cover, at least in degree 0. Again, most of the time they're not, but here it's true. And so from our knowledge of the capital KR, then the lower KR, which is the connective cover, now we know also slices, and basically we just throw away the negative slices. Okay. So I want to display the spectral sequence now. And so let me just first tell you how this is indexed. And to be honest, it's a little bit funny because what we have is, we've defined these fibrations and we can assemble them together and get a tower of fibrations. And this is kind of a standard situation where whenever you have a tower of fibrations, you get a spectral sequence. What you do is you consider the homotopy of the layers in your tower. But usually this is the E1 term. And in at least the way HHR set it up, they call this the E2 term. So that's what I mean. It's a little bit funny. So the point is that there's a re-indexing, which turns out to be convenient, but it's not the indexing that you might initially think of. It's not kind of the standard indexing in this situation. But it turns out to match up with the atoms indexing, and so that's why they went with this. Anyway, so with this particular choice, it turns out that the differential goes to the left by 1. So pi n goes to pi n minus 1. And then we go from the t slice to the t plus r minus 1 slice. And so that's much easier to think about graphically. And so this is kind of the situation. So for instance, and so the homotopy of the various slices will sit along diagonals of slope minus 1. The differentials will all go to the left by 1. And a d4 will go up 4 spots. That means it connects the t slice to the t plus 3 slice. That's fine, but again, so what's nice is that the d4 goes up 4 slots, just like in the atoms spectral sequence. All right, so this is the setup, and now let's just look at what this is in the case of KR. Okay, so this is a picture of the E2 page for KR, and you might say, what the heck? Where does that come from? So this is something that we'll work out in the next lecture, and you'll do it on the problem sets as well. But so for instance, here, this is the homotopy of the 2 slice, right? So the 2 slice, so here we have pi star of the 2 slice. And we know what that is. It's sigma rho of HZ, but we don't know what the homotopy of sigma rho of HZ is. And so I'm claiming that it's these 2 MackieFunctors. So this is pi 1 and this is pi 2. That's what I'm claiming. Okay, so again, these MackieFunctors are here. Here's that sine one we saw before, and here's this geometric one we saw before. Again, we'll talk about this next time, but right now I'm just claiming that this is the correct answer. And so here's the 4 slice, etc. So along all these sort of anti-diagonals, you have the homotopy of the slices. Okay, and now now we have a spectral sequence, which in the end is supposed to give us the answer for the homotopy KR. And one thing we might notice is, hey, I know that both KU and KO don't have anything in degree 3. But here I see a pesky G in degree 3, and that has to go away. Well, there's nowhere for it to go, so it must have been hit by something. And the only thing that could possibly hit it is this Z here. Okay, so that's got to happen just because we know the answer for, oh, right, that's what I just drew. We know the answer for the homotopy. So we have to have this differential, and then by multiplicativity that, that propagates along this diagonal, and so we get all those differentials. And then the eightfold periodicity will tell us this one has to happen too, and we get all of these. Okay, all right, so what happens if after those differentials occur? We're left with an E4 page, which looks like that, and it has no room, it has a horizontal vanishing line, there's no room for any more differentials, and so that's the end of the story. Sort of. I mean, it's the end of the story in the usual sense that a spectral sequence is the end of the story. There are some extension problems left to solve. All right, so pi2, we see these two MackieFunctors here, and the pi2 of KR is some combination of these two, and that's something that the spectral sequence doesn't tell you about, and you have to work out. So again, that'll be something that I'll have you think about on the problem set, but that's the one thing we don't learn from the spectral sequence. All right. Okay, so that's yeah, so that's where we'll stop for today. The plan for next time is to talk about Bourdon homology. I mean, these homotopy of these slices, in fact, these are Bourdon homology calculations of representation spheres, and we'll talk about how you do that. In particular, we'll start with this example, but we'll look at some others as well. And then we'll give the slice filtration in general G. And then we'll look at some examples. In particular, we'll look at some Eilenberg-MacLean spectra and do some examples of the filtration there. This would be obvious in the Postcov filtration, but in the slice, it's not so obvious. So, all right, so that's where we'll end for today.